4차 산업혁명 기획 13주 2차 시간을 시작하겠습니다. 챕터 15는 지구공학입니다. 이번 시간에는 기후변화의 원인인 CO2를 어떻게 캡처할 수 있을지에 대해서 알아보도록 하겠습니다. 먼저 CO2 캡처에 대한 동영상을 보겠습니다.
We rarely witness evolution on a time frame short enough for a single human life to take notice.
진화는 아주 느리게 일어나기 때문에 한 인간의 생애 동안 관찰하기는 어렵습니다.
These changes usually occur over many lifetimes, the gradual drift of a creature's DNA to best survive their environment. But in one case in the 1700s, humans witnessed evolution with their own eyes, and they caused it. This metamorphosis coincided with humans' rapid industrialization.
인간의 빠른 산업화 때문에 진화를 목격한 사례가 있습니다.
We began burning coal on levels never before seen, and its byproducts rapidly changed the landscape for not just humans, but for the animals that shared the planet with them. The peppered moth was one of those animals, getting its name from its speckled white and black coloring, designed to camouflage the moth while it lay on lichen-covered tree barks. A black variant was first observed in 1811, many decades into the Industrial Revolution. At first, the mutation was rare.
공기가 깨끗했을 때에는 얼룩나방의 개체수가 돌연변이인 거뭇나방의 개체수보다 많았습니다.
But humans' influence on the environment grew, and so did their numbers. By 1895, 95% of the peppered moths in Manchester had this black coloring.
인간이 환경을 오염시키면서 맨체스터 지역에서는 거뭇나방이 95%를 차지하게 되었습니다.
Surely this black coloring would leave them exposed, making them easier to spot for hungry birds. In reality, these moths had adapted to be harder to spot in this newly industrialized world, one stained by soot.
오염이 심해지면서 검은색 나방이 새 눈에도 띄기가 어려워졌습니다.
And it may be time for humans to follow their lead, to evolve or die. The rate we have been spewing these pollutants into our atmosphere has only risen since this discovery. Our carbon dioxide emissions have risen from 1,600 million metric tons to 36,000 million metric tons since 1865.
우리가 CO2를 배출하는 것은 16억 톤에서 360억 톤까지 계속해서 증가해 왔습니다.
And despite our best efforts, that number is not declining. Human population and development are continuing to outpace our efforts to curb our carbon dioxide emissions. Just as alcohol-producing yeast will eventually create an environment too toxic for itself to survive, humans are pumping the world's atmosphere with a gas that will eventually render the world unlivable for many, if something is not done.
우리가 CO2에 대해서 무엇인가 하지 않으면 우리는 살 수 없는 지경에 이르게 될 것입니다.
So we have to ask ourselves now, are we going the way of a mindless, single-cell fungi that continue to poison their habitat until they die? Or are we going to recognize that the survival of the next generation is more important? Our previous videos have discussed ways to mitigate climate change by planting trees in the Sahara or by using aerosols to block out the sun. Both are pretty extreme methods and come with some big risks that could lead to some unforeseen consequences. Instead of some risky engineering tactic, what if we could just suck the CO2 right out of the air?
우리는 CO2를 줄이기 위해서 다양한 방법들을 사용할 수 있지만 리스키한 엔지니어링보다 공기에서 CO2를 직접 캡처하는 방법에 대해서 알아보겠습니다.
Undoing some of the damage that has been done. Well, in certain circumstances, this is already happening. Carbon capture and storage has been around for years.
우리가 이야기할 기술은 카본을 캡처하고 저장하는 것입니다.
There are a few main types of carbon capture, almost all of which happens at power plants, capturing the carbon that comes directly from the plant.
공장에서는 많은 카본들이 나올 수 있는데 이것을 직접 캡처하는 것입니다.
The carbon monoxide is reacted with water to produce carbon dioxide, which is captured along with hydrogen. The hydrogen can then be used to produce electricity, and the carbon dioxide is stored. Pre- and post-combustion carbon capture can prevent 80 to 90% of the power plant's carbon emissions from entering the atmosphere.
이러한 카본 캡처를 통해서 공장에서 발생하는 80에서 90% 사이의 카본 에미션을 줄일 수 있습니다.
This is a big deal. The IPCC estimates that carbon capture and storage has the potential to make up between 10 and 55% of the total carbon mitigation effort until the year 2100.
카본 캡처 스토리지로 2010년까지 카본 미티게이션 완화 목표에 10에서 55%까지 달성할 수 있습니다.
However, this carbon has to be stored somewhere. It is most often stored underground in a process called geological sequestration.
문제는 이산화탄소를 지질학적으로 격리하는 것입니다.
Which involves injecting the carbon dioxide into underground rock formations. It is stored as a supercritical fluid, meaning it has properties between those of a gas and a liquid.
CO2는 초임계 유체 상태로 지하에 저장이 됩니다.
When carbon dioxide is injected at depth, it will remain in supercritical condition as long as it stays in excess of 31.1 degrees and at a pressure in excess of 72.9 atmospheres.
저장 조건은 이 온도와 기압 이상이어야 됩니다.
Many times, the carbon dioxide is injected into a reservoir which previously trapped oil and gas, since those areas have natural rock formations that help to contain the carbon dioxide.
많은 경우에 석유와 가스를 저장하던 곳을 사용합니다.
While this might be an okay solution, no one knows for sure what the environmental impact could be if the carbon dioxide were to leak out into the environment in large quantities.
문제는 이곳이 대량으로 새어나올 경우에 환경에 어떤 영향을 미칠지에 대해서 아무도 알지 못한다는 것입니다.
In some instances, leakage of carbon dioxide underground has been shown to increase plant mortality, reduce growth, and create potentially severe localized damage to ecosystems.
생태계에 치명적 영향을 미칠 가능성도 있습니다.
For this to be a viable, safe option, the carbon dioxide would need to remain stored for hundreds of years, or even indefinitely, and the feasibility of this is not certain.
CO2는 100년 혹은 훨씬 더 오래 저장을 해야 되는데 이것이 가능할지에 대해서는 알 수 없습니다.
Other methods of storing carbon include sinking it deep below the ocean, at depths under 3,500 meters, where it turns into a slushy material that will sink to the ocean floor under that amount of pressure.
또 다른 방법으로는 CO2를 3.5km 바닷속에 넣는 것입니다.
But this method is largely untested, and again, there are concerns about what this could mean for marine life, and uncertainty on whether or not the carbon dioxide could eventually make its way back into the environment.
문제는 이 방법이 바닷속 생태계에 어떤 영향을 미칠지 모른다는 것입니다. 또한 CO2가 수면 위로 올라올 수도 있습니다.
There have been more promising experiments in carbon storage in Iceland, where researchers have shown that pumping carbon dioxide into volcanic rock underground can speed up the natural process where the basalts react with the gas to form carbonate minerals, which make up limestone.
또 다른 방법은 CO2를 화산의 바위에 넣어서 석회암을 만드는 과정을 촉진시키는 것입니다.
This is an encouraging development, but it has its limitations. It requires large amounts of water, 25 tons for each ton of carbon dioxide buried, meaning this process would be limited to coastal sites.
문제는 상당한 양의 물을 필요로 하기 때문에 해안과 인접한 곳에서만 할 수 있습니다.
Another is that subterranean microbes might break down carbonate to methane.
미생물을 활용할 수도 있지만 또 다른 그린하우스의 주범인 메테인을 만들어낼 수 있습니다.
Another powerful greenhouse gas. And while 80 to 90% of a power plant's carbon emissions can, in theory, be captured and stored in one of many ways, what about all the other carbon emitting
우리가 설사 공장에서 나오는 카본을 다 캡처한다 해도 다른 곳에서 나오는 카본들이 있습니다.
things in our world? Only 25% of global greenhouse gas emissions come from electricity and heat production at power plants. Transportation, general industry, and agriculture collectively make up around 60% of
그린하우스 가스 에미션의 60%는 자동차와 농업 등 다른 산업에서 나옵니다.
greenhouse gas emissions. Is there a way to capture carbon dioxide from these sources? Direct air capture has, up to recently, been a largely theoretical technique in which carbon dioxide is removed directly from the atmosphere. Theoretical because doing this on a scale that would even make a dent has historically been ridiculously expensive. Some experts say as much as $600 per metric ton of carbon dioxide.
공기 중에서 CO2를 직접 캡처하는 것은 아직 이론 단계인데 1톤당 $600가 소요됩니다.
For reference, a typical passenger vehicle emits about 4.6 metric tons of carbon dioxide per year. But recently, a team of scientists from Harvard University and the Bill Gates funded company Carbon Engineering announced that they have found a method to cheaply pull carbon dioxide pollution out of the atmosphere.
하버드 대학과 빌 게츠가 지원하는 카본 엔지니어링은 공기 중에서 카본을 저가에 캡처할 수 있는 방법을 발견했다고 발표했습니다.
They say for as little as $94 and no more than $232 per metric ton of carbon dioxide. This means it would cost between $1 and $250 to remove the carbon dioxide released by burning a gallon of gasoline in a modern car. And not only do they suck the carbon dioxide out of the air with the ability to store it, they will also transform the carbon back to gasoline or jet fuel.
그들은 낮은 가격에 카본을 캡처할 뿐 아니라 가솔린이나 젯퓨얼로 전환할 것이라고 합니다.
Creating net neutral carbon-based fuels. While this sounds too good to be true, the methods they use to pull carbon dioxide out of the air is not too different from what has already been done for decades.
이 기술은 아주 많은 양의 공기를 빨아들이는 에어 컨트랙터로부터 시작합니다.
This type of direct air capture starts with an air contractor. This structure wet scrubs the air by using a strong hydroxide solution to capture CO2 and convert it into carbonate. The hydroxide solution reacts with carbon dioxide to form carbonate ions. This occurs within a structure which is much the same as an industrial cooling tower.
산업체의 쿨링타워에서도 볼 수 있는 방식인데 CO2를 포함한 공기를 받아들여서 칼륨 이온과 CO3 이온을 만들어냅니다.
Finally, the carbon dioxide is combined with hydrogen and converted into liquid fuels, including gasoline, diesel, and jet fuel, using the Fischer-Tropsch process.
CO3는 몇 단계 프로세스를 거쳐서 CO2 가스가 되고 이는 수소와 결합해서 가솔린, 디젤, 젯퓨얼 같은 것들을 만들어냅니다.
This is a process where a mixture of carbon monoxide and hydrogen are converted into liquid hydrocarbons. This means the company can produce carbon-neutral hydrocarbons.
여기서 카본 뉴트럴, 탄소 중립은 기업이나 개인이 발생시킨 이산화탄소 배출량만큼 흡수량도 늘려서 실질적인 배출량을 0, 제로로 만든다는 개념입니다.
Meaning, if you were to burn this fuel in your car, you would release carbon dioxide pollution out of your exhaust and into the atmosphere, but because this carbon dioxide came from the air in the first place, these emissions would not introduce any new carbon dioxide to the atmosphere.
자동차에서 이 연료를 사용하면 CO2가 나오겠지만 이 연료는 처음부터 공기 중에 CO2로 만들어졌기 때문에 카본 뉴트럴이 되는 것입니다.
And no oil would need to be extracted from the earth to power your car. And perhaps most importantly, for the economic viability of this idea, they can sell the product, which helps offset costs, allowing them to capture even more carbon dioxide.
그들이 이 프로덕트를 팔면 그 돈으로 더 많은 CO2를 공기 중에서 캡처할 것입니다.
To either convert back into hydrocarbons or ultimately store. And backing up their cost estimates of between $94 and $232 per metric ton of carbon dioxide is the fact that they've actually tested the technology in a prototype plant for a few years in Squamish, British Columbia.
그들은 프로토타입 공장을 만들어서 수년 동안 브리티시 콜럼비아에서 운영해 왔습니다.
Which offers a proof of concept that's way stronger than simple calculations or computational models. It currently captures and processes around 1 ton of carbon dioxide per day. However, for this idea to work on a large scale, the process has to be cost effective to implement cheaply around the world.
현재는 하루에 1톤 정도로 프로세스하지만 전 세계적 규모가 되려면 기술이 더 발전하고 가격이 더 내려가야 됩니다.
Without the massive cost of constructing all new factory parts. In the pilot plant, they pulled all of this off by designing a factory based entirely on parts that suppliers could already make cheaply and by keeping careful track of their emissions and costs at each stage of the design and production process. They are currently seeking funding for an industrial scale version of the plant.
현재는 산업화 규모의 공장을 위한 펀딩을 하고 있습니다.
that will use low-cost renewable energy that will produce 200 barrels of synthetic fuel a day, which they hope to complete by 2021.
2021년까지는 신테릭 퓨얼을 만드는 공장을 가동시키기를 희망하고 있습니다.
But how much carbon can they realistically hope to suck out of the air? In 2017, the world emitted about 32.5 gigatons of carbon dioxide. If this technology were built at a scale to suck all that back out of the atmosphere at $93 to $232 per ton, simple math shows that the total cost would be between 3 trillion and 7.5 trillion.
만약 신테릭 퓨얼을 써서 카본 캡처를 한다면 1년에 3조 달러에서 7.5조 달러가 소요될 것입니다.
That seems like a lot, but many industries are worth more than that, including Apple or the airline industry. Definitely a tall order, but not impossible.
결론을 이야기하면 카본 캡처는 아직 비싸지만 불가능하지는 않습니다. 앞으로 기술의 발전함에 따라 공해와 미세먼지가 줄어들고 지구온난화 문제가 해결되는 것을 기대해 보겠습니다. 어펜딕스입니다. 지금까지 시청하신 것으로 이번 차수 수업이 인정됩니다. 그린 세멘트는 건축 분야에서 CO2를 줄이기 위한 노력입니다. 관련 동영상을 보겠습니다.
When we think of things that release carbon dioxide into the atmosphere, we often think cars and factories. But a huge emitter of CO2 that's often overlooked is cement.
Cement is kind of the glue that holds concrete together. And concrete is used more than any other material on the planet other than water.
Concrete is used to build our bridges, our dams, our roads, our sidewalks, even our skyscrapers. This material has helped us build civilizations, but it has also strained our environment in the process. And most of that strain is due to the production of cement, a key ingredient in concrete. For every 1 ton of cement produced, there is a ton of CO2 that is released into the atmosphere. Every year, more than 4 billion tons of cement are produced, accounting for around 8% of global CO2 emissions. To put that in context, if the cement industry were a country, it would be the 3rd largest emitter of CO2 in the world. Atmospheric CO2 levels are directly correlated with rising global temperatures, and both have been rising drastically. If the planet's temperature gets too warm, climate scientists predict bouts of extreme weather, rising sea levels, and scarce food supplies. One company working to reduce the carbon footprint of cement is New Jersey-based startup Solidia Technologies. Solidia says their cement mixture and curing process can cut CO2 emissions by up to 70%. But even if Solidia's technology works, it still faces a major challenge, convincing conventional cement and concrete makers to use it.
Right now, there just aren't a lot of people asking for lower carbon concrete or are willing to pay a premium if there is.
To understand the mechanics of how Solidia's technology works, it's important to first understand the difference between cement and concrete and the conventional process for making each. Cement is usually composed of a mixture of limestone and clay and is one of the ingredients in concrete, along with water, sand, and gravel. The most widely used cement today is known as Portland cement.
Most of the emissions associated with concrete actually occur in the production of the cement. The way that you generally make cement is you mine limestone from the earth, and then you mix it with some other things and heat it up in a kiln to very high temperatures, about 1500 degrees Celsius. Then there's a chemical transformation that takes place, and there's carbon dioxide that's emitted as part of that chemical transformation, and also carbon dioxide emitted with the energy associated with heating up the kiln in which the cement is produced to such high temperatures.
What comes out of the kiln is a substance known as clinker, which is then cooled, ground, and mixed in with limestone to create cement. In order to reduce the carbon footprint of its cement, Solidia Technologies had to slightly alter the chemistry of the mixture. But the process and equipment needed remains largely unchanged.
In order to make Portland cement, you use limestone and sand, you mix it about 2/3, 1/3, and you put it into a kiln that reacts at about 1500 degrees Celsius, so really hot. We take exactly the same raw materials, but we change the recipe a little bit. We mix it about 50-50, and that reaction happens at a much lower temperature, about 1200 degrees Celsius. Now what that means to the cement company is instead of emitting 1 ton of CO2 for every ton of cement, they emit about 40% less than that, and they use 30% less energy to make that same amount of cement. They also get more cement with the same amount of raw materials.
Solidia cement also cures or hardens into concrete differently than Portland cement, reacting with CO2 that the company injects into a drying chamber instead of with water. As the cement hardens, the CO2 becomes trapped in the final concrete product.
When you make Solidia cement, we are cutting the CO2 emissions at least by 30%. And when we cure Solidia cement, when we make the concrete, we add an additional 20-30% of CO2. We consume it during curing. So this adds up to 50-60%, and depending on the formulations, our CO2 savings can go up to 70%.
Another benefit? Solidia helps with water conservation.
The concrete industry uses about 3 trillion liters of water a year. That's about 1 million Olympic swimming pools. Solidia's technology doesn't consume any water, so especially for water-starved areas, India, China, Southern California, we give them the option to be able to recycle their water. When we talk to people in the Mideast, that's actually the #1 thing they want to talk about is water reclaim.
Solidia Technologies also says its product makes financial sense.
We actually find that both on the cement side and the concrete side, if you use our technology, you actually end up saving money. Most of the cost associated with manufacturing cement is in the energy that you use, and we actually reduce that by about 30%, in addition to not having to use a lot of expensive raw materials that they use today. On the concrete side, they don't have a CO2 problem. They don't have a CO2 fee that's going to come attack them. So it really is about performance. And so for us, it's better colors. It's the ability to process it more readily. It's more durable. And I can, instead of curing it in a week or 2 weeks or 3 weeks, it takes us 24 hours. So it's a lot easier for them to get it out in the market. So in the end, we actually are going to save the industry money.
But despite all of this, experts say that there are significant obstacles for Solidia's technology going forward.
Right now, the Solidia product can only be made in a controlled environment. And so as a consequence, they can only make blocks, whereas the vast majority of concrete is ready-mix concrete. And that's what we see in the trucks that are driving around.
Ready-mix concrete accounts for nearly 3/4 of all concrete used. So if Solidia technology is to go mainstream, it needs to find a way to make ready-mix without the need for a strictly controlled environment. It's a problem that Solidia says it's already working to solve.
We're just getting into the market right now. We're doing test pours all around the country and quite frankly in Europe as well. So we're hoping within the next year you'll see us in the ready-mix market as well.
Another big hurdle is code regulations.
This cylinder right here will go into the lab and they'll put a couple 100,000 pounds of force on it, crush it until it breaks, and measure the load, and that gives us a pretty good indication of the performance of that particular concrete mix.
We have to make sure as a company that our technology is validated. It's a 2,000-year-old industry. They really haven't had a new product in a couple of 100 years. So you've got to make sure that industry standards recognize the performance and validate that. So we're working with the Federal Highway Administration in the US, that's DOT. They kind of do the screening for the DOTs, and we're working with several state DOTs to validate the technology with them. But we also work with universities like Purdue, with South Florida, Oregon State, that will take our product and test it under standard testing conditions. But we have to test everything by third parties because nobody's going to believe our data.
One of Solidia's earliest partners and investors is Lafarge Holcim, the largest maker of building materials in the world. Earlier this year, the two companies announced that they would be supplying EP Henry, a New Jersey-based precast concrete manufacturer, with Solidia cement.
Our biggest challenge is this will be a structural material, so it has to pass through certain codes, you have to get certified, and this is a long process. So initially we chose products that doesn't really require very intensive code or regulations, so that's why we picked pavers and blocks. They are easiest to the market.
Solidia Technologies is not alone in trying to reduce the carbon footprint of cement. In fact, the green cement market is expected to grow significantly from $21 billion in 2018 to $43 billion by 2026. Other companies working on green cement technology include Blue Planet, CarbonCure, and Carbicrete. Unlike Solidia Technologies, Carbicrete does away with the need for cement in concrete altogether by replacing it with steel slag, a byproduct of steelmaking. This new mix is poured into molds like conventional concrete and cured with CO2. And it's not just companies taking up the call to action. Academics are weighing in too. Despite all their work with perfecting the cement formula, Solidia says it's not trying to become a concrete maker.
Our mission as a company is to help others reduce their footprint. There are plenty of people that do a great job making cement. There are plenty of people that do a great job making concrete. Us adding capacity to that actually will slow down the process because you need a lot of money to spread this all around the world. So we're really focused on helping them transition to this new technology because we think that's going to be the fastest way to get us into the market.
If Solidia Technologies is able to convince the major players in the multi-billion-dollar cement and concrete market to use its technology, it could have a significant impact on our environment. The company says global adoption of Solidia products would reduce CO2 emissions by 4% per year. That is double the CO2 savings that we would get if we grounded the entire aviation industry. Solidia also says it would reduce energy consumption by as much as 260 million barrels of oil and save 3 trillion liters of fresh water per year.
We know that Solidia is scalable because we've already worked with the largest cement company in the world, LafargeHolcim, to help us basically prove that they can make our cement anywhere in the world on any existing kiln with the raw materials they have today. So we know we can do it on the cement side. On the concrete side, we're not changing their mixing process, we're not changing how they put it into a mold or a form, we're just changing the way that it reacts. Instead of putting water in, we put CO2 in. So we have to make a little bit of a change there, but not enough so that it really disrupts their current operating process. So we feel pretty good about the ability to scale it.